Okay, hi everybody. This is Dr. B, and let's talk about the aldol condensation lab. The aldol condensation comes from the name of an aldehyde reacting and turning into an alcohol. We have an aldehyde here, and in the presence of a strong base, it could react with itself. In other words, this has acidic hydrogens. Anytime you have a carbonyl group, look for a CH next door. If you see one, that H is susceptible to loss in the presence of a strong base, such as sodium hydroxide. Now, once that does form that negative charge, normally that couldn't happen, but if you have a carbonyl group next to it, it will be resonance stabilized. That minus charge can form a double bond there, kick out and form an O minus, moving the minus charge from here to here. That spreads it out, that makes it more stable, that means it can form more easily, and once it does that, it will go around looking for something with a positive charge, and it could react with itself. And that can give you a beta hydroxy carbonyl group, in this case an aldehyde. So that shows that reacting with itself, and that's the classical aldol condensation. Once this thing forms the alkoxide, it can then protonate, and you've got your beta hydroxyaldehyde. Watch this YouTube video if you'd like to learn more about it. If you want to do a mixed aldol reaction, if you have one substance that can form the enolate anion and another carbonyl group, you can have this form its enolate, the negative charge right there by adding a strong base. We're using sodium hydroxide here. That negative charge, if it's all formed, and there's no other carbonyl group to react with, will then go seeking this carbonyl group present in benzaldehyde, and it'll give you another beta hydroxycarbonyl group, beta hydroxyaldehyde, that looks like this. Now, if these are arranged like this, oftentimes they very easily can lose a molecule of water so that it goes fully into conjugation. You lose OH here and an H there, you get a double bond. And look at this extended conjugation. All these double bonds are alternating right through the carbonyl group. When you see extended alternating double bonds ending in a heteroatom like O or N, usually means you have a colored compound, perhaps yellow, for example. So that's a mixed aldol. And what we're going to do today is synthesize dibenzyl acetone. This is a mixed aldol condensation of benzaldehyde with acetone. This sometimes is known as the Claisen-Schmidt reaction. Let's analyze this thing and see how this plus this can turn into this. I would start by asking myself which one of these would react with our strong base. And I don't think this one can. This is a carbonyl group right here, but on one side we do not have a CH, we only have an H. And on the other side we don't have a CH, we have all four bonds taken up here, so we just have a C. I don't see any very acidic hydrogens there, but on this one I do on both sides. It can form CH2 minus here, that's one enolate, react with benzaldehyde, and then it can go ahead and do the same thing on the other side. Once both of them condense and push off water, you end up with dibenzyl acetone. So if that made sense, you can understand how 2 moles of benzaldehyde will react with each mole of acetone to make 1 mole of dibenzyl acetone. Here's the amounts that are being used. We have only 0.2 of a gram of benzaldehyde, which is 2 millimoles. We have less than 100 milligrams of acetone, and we're using it's 58 milligrams, which is exactly 1 millimole. We have exactly twice as many molecules of benzaldehyde as we do of acetone. So in theory, nothing is limiting, nothing is excess. We have exactly 2 equivalents and 1 equivalent. So 2 of these plus 1 of these makes 1 of these. So we should end up with 1 millimole of product. It's got a molecular weight of 234. So 1/1000th of that is 0.234. That's the number of grams we'll get. So we have a theoretical yield of 234 milligrams. And here's the mechanism. Acetone will react with base. It'll pull off one of these hydrogens to form the anion here, which is resonance stabilized to form the enolate anion. And therefore, once this loses its water, it will seek out something with a positive charge. The carbonyl carbon of benzaldehyde is a great example, and it will react with benzaldehyde, form the alkoxide. That alkoxide does have water present, so it can easily protonate, and now you've got your beta hydroxyketone. In some cases, it would just stop there, but when it can go into extended conjugation by losing water here, this OH minus, this base is strong enough to deprotonate here, form the double bond, lose a molecule of water, kick out hydroxide there, and you've got your half your product. We do not show the mechanism of the second half, but I bet you can imagine. I'll say the words in case it helps. Loses H plus to form CH2 minus, seeks out a benzaldehyde molecule right here, and then the mechanism here is identical. It's just on this side rather than the other side, and you'll end up with dibenzyl acetone. Here's the actual procedure. Grab yourself a 1 ml reaction tube, add to it some 3 molar sodium hydroxide, that's a good strong base. Add a little bit of 95% ethanol, that's a solvent that is chosen so that everything mixes together nicely, but the product will crash out when it's done. Throw in your 0.212 grams of benzaldehyde, that's 2 equivalents, and go ahead and add your 58 milligrams of acetone. So little acetone. That's the stuff we wash our glassware with. And we're measuring out 58 milligrams of it. And we add it to 1.6 mils of ethanol. Drip it all together. Mix all reagents well. Shake it forever, 30 minutes. This is a modification. If you're writing up the lab report, we always list our modifications to the standard procedure. The reaction will happen. Good to know. Benzaldehyde will go into solution. You'll get a pale yellow solution resulting, and a cloudy yellow precipitate should form. Remember, we predicted the product would have a yellow color by that extended conjugation ending in a heteroatom. Step 4. Let's take 3 mils of water, add it, shake it around. I think that's to remove that extremely strong base that we had in there. And so shake it around, remove the liquids, not the solids. Do it another time until it's not so nasty. It's a little closer to plain old water present. Vacuum filter it. So that means collect your product. You should see a nice yellow solid. But it's going to have a yield at that point. The crude yield will probably almost certainly be over 100%. And after a whole week of drying, you should have a nice dry solid. And here's the actual recorded amount of product that you got, 101 milligrams. Turn that into a percent yield and you should be good to go. Okay, that is the mixed aldol condensation, otherwise known as the Claisen-Schmidt reaction. I hope that's enough information for you guys to write an awesome lab report. We do not have the scoring guide yet, but I will add it to the materials section of Blackboard. Email me if you have any questions. Stay healthy, everybody, and we'll see you next week.